Okay, then before I begin my talk, and because of what Herbert just said, maybe just let me briefly explain why I want to be talking about something unscientific as consciousness. The idea is that, engineers are currently already building neuromorphic chips and neuromorphic hardware, and what I'm trying to assess is how high is the risk of them actually creating something like artificial consciousness. For example, if you remember, Thomas Metzinger, for example, had very similar thoughts, and he's been worried of a suffering explosion, of what he called a suffering explosion, which means that researchers are by chance or accidentally building artificial systems which are capable of suffering. And he thinks that we should press pause on current research and kind of better think about what artificial consciousness is. What I want to do is I just want to take a closer look at neuromorphic engineering and assess how high those risks are that Thomas Metzinger is talking about. But that's already it. The title of my talk is Neuromorphic AI, from simulating towards replicating the brain. And what I want to be doing in this talk is twofold. First, I want to give an account of what a simulation is when compared to what a replication is. And in the second part, I want to closely look at neuromorphic hardware and see whether it might become a replication and whether it therefore is more likely that neuromorphic computers might become conscious. The main thesis that I want to be defending is this: artificial neural nets running on neuromorphic hardware are more likely to generate artificial consciousness than simulations on standard digital hardware. Okay, maybe just let me briefly explain where those thoughts are coming from. The first kind of thoughts like that I had when reading Searle's famous 1980 paper Minds, Machines and Programs, where he writes, "No one supposes that a computer simulation of a 5-alarm fire will burn the neighborhood down, or that a computer simulation of a rainstorm will leave us all drenched. Why on earth would anybody suppose that a computer simulation of understanding actually understood anything, or that a computer simulation of consciousness actually was conscious? To confuse simulation with duplication is the same mistake whether it is pain, love, cognition, fires, or rainstorms." And to me that made perfect sense. I was thinking if we want to build something that could actually fly, it is not enough to simulate a bird, but we need to replicate it and build actual planes. Or if we want something that is capable of pumping blood, it's not enough to simulate a biological heart, but we need to replicate it in some sort. And that debate carries over to the modern debate on consciousness as well. Piccinini, for example, writes in his 2021 paper, "Most of the options on the metaphysics of consciousness entail that a genuine brain replacement would be conscious, while a brain simulation would not be conscious." So I think what Piccinini here calls a brain replacement and Searle calls a duplication and what I call a replication, that's all the same idea. And like I said, that kind of made sense to me. And I was thinking, okay, well, what would it mean to build a brain replication? You probably have to kind of build some artificial neurons, then build maybe artificial synapses, and then wire them together and build an artificial neural net from them. So that's probably what it comes down to being a brain replication. Then I was thinking, well, isn't that kind of what neuromorphic engineering is doing? Aren't they building artificial neural nets from actual artificial neurons that are wired together in a brain-like structure? And I thought, yeah, well, that kind of makes sense. And then I went to sleep, and the next morning I woke up and I thought, well, no, that's all nonsense. Neuromorphic hardware is just a different kind of hardware, and let's be fair, neuromorphic chips don't really look like brains in a certain way. And I thought, that's all nonsense. And I kind of kept oscillating between those two positions. And that's when I understood that I didn't really know what it means to be a replication of a brain, or a replication of anything for that matter. So what I want to do now is give a clear definition of what it might mean to be a simulation and to be a replication, which is more important. Those are the definitions. A simulation is a physical system that implements a model, which I think is kind of straightforward. And a replication is any real-world phenomenon that the model is a model of. I will be talking about what exactly that means in just a minute. Maybe two things to notice here. First, both simulations and replications are physical systems. They are physical systems, concrete physical systems when compared to abstract programs, for example. And the second, what will be important is the concept of a model. So what I will start out with is just giving a brief overview or a brief definition of what a model is. A model, for example, the one you can see here, which is the so-called Drossel-Schwabel forest fire model, which models the spread of a forest fire. I have a little video here of how to envision that. You can see it shows how the fire front spreads over time, or how the fire front evolves over time. Show it again. And what is a model? A model, at least on my account, is a mathematical structure together with an interpretation. I think that's fairly standard. Let's quickly look at what that means. The mathematical structure you can see here on the right hand side. In the case of the forest fire model, it is an cellular automaton, but it could be anything from a differential equation to an algorithm to whatnot. That's the mathematical structure, and to make it a model of something, we need to somehow connect the abstract mathematical structure to the real world. And how do we do that? I think we should do that by assignment and explanation, by assigning how the world connects to the states of the model. The assignment of a model is the specification of how parts of the world are connected to the states of the model. Well, what does that mean? Let's go back to the forest fire model. Those cells here have three different states, 0, 1 and 2. And in order to make it a model of a forest fire, we need to specify what those states stand for. And those are healthy trees. One you can see here represented by a 1. Burn-in trees represented by 2s, and burn trees represented by 0s. So we need to say what the states stand for. Healthy trees, burn-in trees, and burn trees. That's the assignment criterion. And what I think is required additionally is an explanation. The explanation of a model specifies how the causal laws of the real-world phenomenon are connected to the state transition rules of the model. Again, what does that mean with respect to our forest fire model? Those here are the state transition rules. You can see, well, if a cell is in state 1 and if there is a burn-in tree in its surrounding, in the neighboring cells, this 1 is going to turn to a 2 in the next time step. And now we need to explain why this state transition rule is a sensible state transition rule. And in our case, the laws that explain this state transition rules are the laws of thermodynamics and heat transfer. And why is that? Well, we explain that state transition rule by saying, well, okay, in the real world, burn-in trees set neighboring trees on fire within such and such a time frame because of the laws of heat transfer and thermodynamics. Those laws explain why it makes sense to use this state transition rule. That's what I call the explanation. Okay, and now if we want to build a proper replication, for example, of that forest fire model, the assignment and the explanation need to be fulfilled as well. And why? Well, I defined a replication to be any real-world phenomenon that the model is a model of. And now it kind of makes sense to define an assignment criterion and an explanation criterion in order to be a system that the model is a model of. The given physical system needs to be the kind of thing or the sort of thing that the model is assigned to. In the case of a forest fire model, in order to be the thing the model is a model of, it needs to fulfill the assignment criterion, meaning it needs to consist of healthy trees, burn-in trees, and burn trees. That's the assignment criterion. Additionally, the system needs to be governed by the causal laws that the model uses for explanation. Remember the causal laws that the Drossel-Schwabel forest fire model uses for explanation are the laws of heat transfer and thermodynamics. Let's go back. For example, this forest fire here, which obviously is a proper replication of the forest fire model, it not only consists of healthy trees, burn-in trees, and burn trees, but the fire spreads because of the laws of thermodynamics and heat transfer. This tree is going to set that tree alight within a certain time frame. Those are the assignment and the explanation criteria. And a simulation now is either not the thing the model is about, or not governed by the right causal laws, which means it either fails the assignment or the explanation criterion. Here we can see an example of a model of a system that meets the explanation criterion, however fails the assignment criterion. Imagine the following scenario. We take a couple of matches and arrange them in a chessboard-like structure. Then we start burning the first tree, setting the first match alight, and then just watch how the fire spreads. The fire spreads according or because of the laws of thermodynamics and heat transfer. The burning match burns down the next one. And therefore, this system meets the explanation criterion. However, obviously it does not consist of trees, therefore it fails the assignment criterion. But it could go the other way around as well. in this case, we have a model that meets the assignment criterion, however, fails the explanation criterion. Imagine the following scenario. We have a farmer who tries to illegally gain some farming land by burning down the forest in on his land. But in order to cover up for his delinquency, he tries to make it look as if it were a natural forest fire. And therefore, he does not just randomly burn down trees, but he starts with one and then starts burning trees that are in the neighboring, in the neighborhood of that already burning tree. So the fire in that case spreads according to the according to the mathematical structure as given by the Drossel-Schwabel model. The real-world physical system under consideration does consist of healthy trees, burning trees, and burnt trees. Like the farmer is burning down real trees, so it meets the assignment criterion. However, this system fails the explanation criterion because the fire spreads the way it does, not because of the laws of heat transfer and thermodynamics. Imagine it had rained the day before and the fire just doesn't spread, but because the farmer intentionally sets trees on fire. So this system meets the explanation, the assignment, however, not the explanation criteria. Okay, and from what I've said so far, it kind of sounds like a real replication of a natural phenomenon must itself be a natural phenomenon. But this is not the case. For example, we could build an artificial replication of the forest fire model, of the Drossel-Schwabel model. Just imagine that case. We go to a gardener, buy a couple of tree saplings, and then arrange them in a chessboard-like structure, just as in the match case. And then in that grid of trees, we pick out one and set it on fire, and then just watch how the fire spreads. And this now would be an artificial replication of the forest fire model. And you easily can see why. Just check first, it meets the assignment criterion. It consists of actual trees, which are burned and healthy. And the fire spreads due to the laws of heat transfer and thermodynamics. So this now would be an artificial replication. So artificial replications indeed are possible. Okay. So, and now what I'm trying to convince you of is that compared to simulations, replications share more properties with the target phenomenon. Again, let's look at the forest fire model. Imagine we want to model a forest fire, let's say in the north of Brandenburg, and we use the Drossel-Schwabel model. First, we build a simulation, just like the one I showed you before. And then we build a replication, imagine the tree sapling replication, and let's now look at what properties simulation and replication share with the original target phenomenon. The real forest fire has a couple of properties. For example, it implements the cellular automaton. That's why the Drossel-Schwabel model is a model of the forest fire. It is heating up the environment at the fire front. That's what Searle meant when he says that 5-alarm fires burn the neighborhood down. And the real forest is also cooling the environment in the forest area, in the area of healthy trees. That's what forests do, they lower the ambient temperature. That particular forest fire additionally is located in northern Brandenburg, has an area of, 200 hectares, let's say. It causes people to leave their houses, etc. On the other hand, if we look at the simulation, the one I showed you, it has almost none of those properties. It is implementing the cellular automaton. That's why it is in simulation. But it obviously is not heating up the environment, it is not cooling the environment in the forest area, and it's also not located in Northern Brandenburg, but here in Osnabrück. And it doesn't have the size of 200 hectare, etc. The replication, on the other hand, does share a couple of properties with the real forest fire. It actually shares quite a lot of properties with the real forest fire. It is implementing the cellular automaton. It is heating up the environment at the fire front. Again, think of the tree saplings, the burn in tree saplings. And it is cooling the environment at the forest area. So the tree saplings also lower the ambient temperature. However, it does not share all the properties with the real forest fire. Obviously, it's not located in Northern Brandenburg, at least not necessarily. It also probably does not have the size of 200 hectare, and it also doesn't cause people to leave their houses. And this now must be so. A replication necessarily shares those properties with the target phenomenon. And if we think of the assignment and the explanation criterion, it's easy to imagine why that must be the case. Any system that is governed by the laws of thermodynamics and heat transfer, that is, meets the explanation criterion of the forest fire model, must be heating the environment at the fire front. That's what it means to evolve due to the laws of thermodynamics and heat transfer. Additionally, every system that consists of actual trees, which are sufficiently densely populated, must be cooling the environment at the forest area. So every system that meets the assignment criterion and the explanation criterion, that is replication, must have those properties, must share those properties with the target phenomenon. So I think the takeaway here is that unlike simulations, replications share quite a lot of properties with the actual target phenomenon. Okay. Maybe so much for replications and simulations. Let's now look at neuromorphic hardware and ask the question of whether they are replications of brains in the sense stated above. Well, if we want to know if neuromorphic hardware or neuromorphic chips are replications of brains or of brain models, we need to check whether they meet the assignment criterion or whether they meet the explanation criterion. So let's start with the assignment criterion. Brain models probably are models of neurons and synapses. So we need to see whether neuromorphic chips actually consist of neurons and synapses. So let's take a look at what neurons are. Here we have a definition. Neurons are cells which are specialized for the generation, conduction and transmission of electrical signals. So we have both a morphological and a functional definition, or let's say this definition has a morphological and a functional part. The morphological part states that they must be cells, and the functional part states that they must be transmitting electrical signals. And now, unfortunately, and due to the morphological criterion, or due to the morphological part of the definition, artificial neurons, as used in neuromorphic hardware, are not real neurons. They are not cells, and therefore, strictly speaking, neuromorphic chips fail to meet the assignment criteria. However, artificial neurons, even though they are not proper cells, they are what biologists call functional analogs of real neurons. That is, they are at least capable of performing or of having the same function as real neurons. Three functions of neurons which are plausible candidates, or three things that are plausible candidates of being the functions of neurons, the biological functions, is 1, information processing, 2, information integration, like biological neurons physically integrate information, not only process it, and 3, electrical signaling or spiking. And I think certain artificial neurons in that sense actually are functional analogs of biological neurons. For example, here on the right hand side you can see on the right here the spiking behavior or the electrical signaling behavior or the response behavior of an actual biological neuron from the neocortex, I think. And on the left hand side you can see the spiking behavior of an artificial silicon neuron. And as you can see, those are almost identical. And therefore I think it is fair to say that at least this kind of artificial neuron is a functional analog of a biological neuron. And for artificial synapses, I think we can make a similar argument or a similar case. Here we can see, well, on the left we see a biological synapse, and here on the right we can see an artificial synapse that reacts on dopamine release. So if you release dopamine, it changes the conductivity down here. So I think that's, functionally speaking, pretty much what a biological neuron, what a biological synapse does. So this, at least arguably, also is a functional analog of a biological synapse. Now let's look at the explanation criteria. Here I must confess I'm not so certain on whether they meet the explanation criterion. This is because I'm not quite sure what the relevant neural mechanisms are, and also I'm not so sure on which of those mechanisms already can be emulated in neuromorphic chips. So you definitely can debate me on that, but I try to argue that at least some neuromorphic chips do meet the explanation criterion, at least arguably. And why do I think that? Neuromorphic chips copy some neuromechanisms, including synaptic plasticity, which means they actually adapt the synaptic strength depending on which spiking signals they receive. They also, like as we've heard before, have very similar neural membrane dynamics as biological neurons. And some neuromorphic chips, for example the one here by Agarwal et al., they use actual ion transport mechanisms via chemical gradients for processing. So I think, like I said, you can debate me on that, but I think it's fair to say that some neuromorphic chips actually meet the explanation criteria. Okay, so where are we? I try to argue that even though neuromorphic chips, strictly speaking, fail the explanation criterion because they do not consist of real neurons, they go towards meeting the assignment criterion because they consist of functional analogs of real neurons. And 2, I try to argue for neuromorphic chips being meeting the explanation criterion. So I think it is fair to say that neuromorphic chips go towards replicating the brain. Are not quite there yet, but they go towards replicating the brain. And here comes the argument. Premise 1. Replications share more properties with the target phenomenon than simulations. That's what I was trying to argue for in the first part of my talk. Like replications of forest fires share more properties with real forest fires than simulations. Replications of brains share more properties with brains than simulations. Premise 2, brains are conscious. I don't think many would debate me on that. And from this it follows that replications of brains are more likely to be conscious than simulations of brains. Conclusion 1. The next premise, standard digital hardware cannot go beyond simulating brains. I did not argue for that, but I take it as a given, which is just due to the huge differences, physically speaking, between a laptop, for example, and a brain, or a computer and a brain. Premise 4, artificial neural nets running on neuromorphic hardware are moving towards being replications of brains. That's what I was trying to argue for in the last part of my talk. They go towards meeting the Simon criterion, they meet the explanation criterion, therefore they are moving towards being replications of brains. And if you believe what I've said so far, from this it follows that artificial neural nets running on neuromorphic hardware are more likely to generate artificial consciousness than simulations on standard digital hardware. That's the point I was trying to make. Those are my references, and if you have any questions, feel free to ask. Thank you very much for your attention.